What if there was a way to reduce the energy costs in mine sites by 90%? Effectively unlocking the potential of many mines that are today unviable, making energy clean, and solving one of the biggest challenges today in mining. I'm Hayden Smith, I'm CEO of FEX Energy, and we're building the world's first high-density energy storage system based on iron. So how many of you knew you could store energy in iron? Marco knows, because we've talked. But I mean, iron is this ubiquitous material, the most produced metal in the world, the fourth most abundant earth element. And if you want to make an energy storage effective, then you really want to base it on something that's abundant. So we're turning this base element that has been seen as a material supply for the world into a way of unlocking energy for the world as well. Our company is a Montreal-based clean tech startup. We just closed the seed round. Totally, we've raised about $8 million. And what we're building is a solution, as I said, based on iron that is thermochemical redox. So we're storing the energy chemically in the iron, releasing it as heat. So that solves some problems because we can do heat and power, and we'll talk more about that. We're a really cool team of now 13 people, have grown from an initial founding team of 6. We've got really great scientific expertise. My background is actually from the corporate world. I worked at Siemens Energy, was co-founder of their venture arm. And I've seen too much in the world, an absence of the ability to innovate, corporations sometimes holding back people. And two and a half years ago, decided to start this company as an answer to that. I had all kinds of ideas and talent and met some really cool innovators. So we put this together to bring this technology to fruition. So we've got some wonderful partners, including Mika, obviously, and we're really well poised to turn this technology into something impactful for the world. What's the problem that we're solving? In mining, energy is scarce and it's also wasted. So something like 50% of operating costs for mines are in energy use. And that energy often comes from peak power. About 75% of energy costs come from the peak of demand of power. And sadly, 98% or so of that energy is wasted. We heard all about the crushing and the waste heat that actually gets generated by that. So we're using a lot of energy. It's very expensive. In remote sites, it's using diesel, which is dirty, which is complex. And we're also wasting quite a lot of it. Most of it actually ends in waste. So the solution that we're developing is one that reduces energy costs and makes more out of that energy. It actually shaves the peak power demand by shifting peaks, as you can see on the graph on the left. The idea there being that we can shift the time of use of energy on an hour basis, on a day basis, or even on a season basis. Meaning when there's an abundance of energy, we can take that, store it, and then shift it to when it's not available. That effectively reduces the cost of that energy, and it frees up capacity for other applications in the mine site. It turns mines that are potentially unviable into ones that are. And we can also store waste heat, turning that wasted energy back into something useful. This all centers on the premise, the first principle, that the sun puts out enough energy in 90 minutes to power our world for a year. So there's really no reason why we have to be going to exotic energy sources that take a lot of energy to get out of the ground, to move to sites and to use. We can actually harness the sun and the wind's energy, the wind just being a secondary effect of the sun, to generate all of the power that we need for applications around the world. Obviously, the challenge is the sun and the wind are not always available. So that's where storage comes in. And this is a $4 trillion market up to 2040. Experts say. So it's long-duration energy storage is something that's absolutely needed. I just came back from Australia as an example, where miners there are actively looking for storage solutions that can store the sun's energy and make that ubiquitously available at a very low cost. So how do we do this? I mean, I talked about iron as being the material that we're storing energy in. And if you look at materials across the board, which is exactly what our professor, who's also our chief scientific advisor, Jeff Berg-Thorson did, something like 10, 15 years ago, he said, if we're gonna make an energy storage system, what should we make it out of? And the two criteria he looked for were density and abundance. You want a material that's not going to have bottlenecks, the whole critical mineral supply thing that we're talking about. You want something that's widely available, and you want something that can store energy in a small unit per volume. So iron, if you look at it compared to even diesel, is actually 60% more dense as an energy carrier. If you compare it to other emerging energy storage solutions like hydrogen, thermal energy storage, batteries that exist today like lithium ion, we're talking about 10 to 100 times more density in the energy that it can carry. Obviously, it's a vastly produced metal, and at scale, we would only need something like 0.1% or 0.01% of the world's iron supply. So there's no risk of supply chain shortages. There's no risks of cost increases as a result of the use of this material. It's stable, so we can store energy for days, weeks, even months, as we've talked about. So that's another really core criteria for making an energy storage solution. And it's safe. Iron's not toxic, it's not flammable or combustible, it doesn't have an explosivity risk. So we have this really amazing element that can turn into an energy storage solution. And you might ask, how do you do that, right? Because it's great that iron can store energy, but how do you get the energy out? How do you put the energy back in? And that is, in essence, the essence of our solution. Call it the iron arc reactor. This is a cell that, in essence, stores energy through a reduction process, as you see on the right, taking abundant clean energy and converting iron oxide back into iron. That's a process that's very similar to direct reduction. That's about 10% of iron production today is made in that way. That's done in the box, so we have all of the equipment to enable that. And then the oxidation cycle is how we release the energy. So we flow air over the iron at the right conditions, and that oxidizes the iron, which is, of course, an exothermic reaction, releases heat, and that heat comes out at up to 900 degrees C. So in general, in totality, when you take that cell and you put that in a box with the balance of plant, what you get is a system that stores energy just by putting clean electricity in and discharges heat by putting air in. And what comes out is that heat at 900 degrees C. It's an oxygen-depleted air, basically. So that's actually good for some processes. We can talk more about that. But you can convert that air to many things, including hot glycol, steam, power, even through a steam turbine. So what you get out of this solution is a highly affordable solution because of the low cost of capital based around this iron energy storage and the density, which requires little material to actually make. You get a solution that can actually reduce the cost of energy substantially and therefore pay back pretty quickly. We'll talk more about some use cases around that. But also importantly is that the solution itself is very dense. So we're talking about 1/10 of the footprint or so of lithium-ion batteries, so 35 megawatt hours per 40-foot shipping container. And that's important because deployability in a remote mine site, for example, is a challenge. Setting stuff up on site, plugging things in. The amount of construction obviously is very, very expensive when it's the more remote you are. So the density matters in that case. The safety, non-toxic, non-corrosive, we talked about. Plug and play, easy to set up, and proven subsystems. So the balance of plant, about 90% or so of the bill of materials is proven off-the-shelf hardware. The novelty, our reactor, is what is being developed. So how does this actually integrate and add value to a mine site? So integration, as I said before, would be with clean electricity, whether that's in a grid-tied last mile mine site. We're taking energy off the grid. We're charging when that energy is available. So when we're not at a sort of peak limitation on power capacity. And then we're storing that energy and discharging it as heat. So the heat can come out in a couple of ways. On the top, the 900 degrees C air, oxygen-depleted air, can be used for drying, for other processes in the mineral world. Can also convert to heat through a heat exchanger. Glycol, for example, in a heat loop that could power a mine site's mine shaft heating, buildings. We'll talk more about the integration of that in a second. And then sort of power applications as well, where we can convert the heat to power and, again, shave the peak power need for the site. So you see some examples there. Waste heat can come back in. So the way we charge, you saw before, we take clean electricity. Some of that clean electricity is used to actually make heat through resistive heaters. If we have heat available from a secondary source, a waste source, we can just reduce the amount of electricity needed to generate that heat. So some potential applications in the mining world. We've been looking at mining as an industry to address for about a year. We've seen this as a really important industry because actually mining is the biggest consumer of high-cost fuels. About 10% or so of final energy use is in diesel, propane, and other high-cost fuels, much of that used by the mining world. So we've seen applications like cold climate in Canada, obviously. We have very cold weather. In sites, the more north you are, the more cold it gets. Agnico, for example, have a real challenge around heating in the winter, keeping mine shafts hot, keeping buildings warm, milling equipment from freezing. All of those things require a lot of energy, often makes up actually the peak demand over the year. So we can heat equipment, for example. We can do process heating, so heating and drying or concentration. Leaching, we heard a lot about copper and leaching and trying to increase productivity. BHP, for example, we're working with them to explore a leaching operation in Chile, some of their mines there, where actually the heat addition from our products stored from renewable sources could increase productivity and the output from those leach pools. So that's another potential application. And obviously combined heat and power, we can store that energy, release it as electricity, and use that to sort of shave the peak demand from hoists on shift changes, for example, or for mills, for example. Electrification of vehicle fleets is another potential application there. So just an example, this is really a highly economic solution that makes especially remote sites energy costs come down. And you can see how we've basically articulated this in the graph on the right. Shows the baseline cost. That thumb sticking up on the left is basically the cost of fuel today. This is propane as an example. Diesel can be even more expensive, and I think the levelized cost of energy is around 30 cents a kilowatt hour. And if there is an abundant source of renewable electricity on site, we can charge and we can store that energy for about 5 cents a kilowatt hour. And so that basically reduces your effective cost by up to 90%. If you have to build the renewable assets on site, even in Canada, we're talking about 10 to 15 cents a kilowatt hour for electricity from renewable generation sources like wind in the most remote places in Canada. So that is still substantially less. Add to that the 5 cents from our product, and you still have a substantial cost savings. So we're talking about a sort of 1 to 4 year payback on capital costs, hundreds of kilotons of carbon abatement over the life of the solution, and all that fitting in about a tenth of the footprint of lithium ion. You can see the picture on the left that sort of showcases how the solution would be small, very relatively compared to lithium-ion batteries. So our roadmap, what we're building to commercialize this technology is taking the technology that is today at a POC level in the lab and turning that into a pilot. We've closed our seed round, as I've mentioned, so that gives us the capital we need to build this pilot. We have an exciting partnership with FEX Energy to build this pilot to deploy on their site in Ottawa, to abate about 100 kilowatts of peak heating demand for their site in a similar sort of fashion to how it will operate on a mine site in a district heat system. And we're surrounding that pilot with partners as well. So we're open to development partnership. We have already BHP signed up to be part of that, and we're happy to talk to other people as well to explore how that can help us to move this forward. Not just to move it forward, but to move it forward in the right application. Life is too short to build something nobody wants, but if you work with the people that actually want it, you'll develop something that's valuable for them. And that's really our whole modus operandi. And our intent is to start commercializing the solution and making first deployments from 27 or so. So just a last word on this opportunity for development partnership. Most startups are looking to commercialize and then sell their product to first adopters. We're looking to bring first adopters into our pilot program. So you have an opportunity, should you want to join this pilot, to actually work on the development of the technology with us, to frame use cases and tests that we could actually operate on the pilot, to demonstrate the value for this solution to your operation. I mean, that would be demonstrating the performance that it could operate at scale, on a obviously smaller scale, demonstrating the economics of how it could really save money and add value for your organization. So that's what we're trying to build. We're looking for 2 or 3 other partners to join with the ones that we've already developed. We have an amazing team, as I mentioned sort of before, about 13 people today that have a mix of experience from the R&D world, and energy development and production development, product development, also from the world of mining, a couple of people that now have really given us an insight into what this market really needs. So we're really excited to make this real. We're looking for development partners. We have an awesome team and awesome tech. And we'd love to talk more if you're interested to be part of this with us. Thank you so much.
Okay, thanks, Hayden.
Pleasure.
So I got a multi-part question Yeah, but they're all simple questions. So my multiple question starts off with this. So, is there any risk of this technology exploding on someone? I mean, are there any off gases that come out of it? Can it be put in a building? Can you have people sitting around it? So that's kind of one part of the question.
Yeah.
Then the other question is, does the cell deplete over time? Like, is there a time that comes when the cell is not as efficient as it was, when you first installed it? Maybe I'll leave it at those questions.
You're testing my memory now. I have to remember everything said. So the answer to the first question is no, yes. So the first A, B, and C there. So the first part of your question was, is there any safety concerns? Does it blow up? You know about the Lac Mégantic disaster that happened in Quebec a few years ago? Those tanker cars that were carrying oil tipped over and had like a terrible disaster as a result of that. Imagine that same train car carrying iron in containers. Had that thing tipped over, you would have had a bunch of iron on the ground to sweep up and put back in. So the risk of iron actually creating a mega disaster of that order is very, very little, if not nil. You have to disperse powder very, very finely. The powders we use are also not very fine, so there's not a propensity for that kind of a release. Yes, you could put it in buildings. We'll work on certification, so the certification will be the enabler to demonstrate and to make that possible. This is a new category. There's no competitors in this space, sort of blue ocean. So CanMed is actually a wonderful partner, and they have some of the CSA people that are actually regulating and developing standards for these things. So we're going to work with them and try and develop standards that make sense for our product. The second part of your question was around depletion over time. So this is actually the biggest technical challenge. It's the core of the IP. What we've been able to do is actually demonstrate the redox cycle many, many times over. And what we've seen is actually, and this is all about the way we've done this and the IP we've generated, is a sort of self-healing effect in the cycles. So the challenge there is, do you have mechanical cracking changes in the actual morphology of the iron? Those of you that are working in the DRI world, you understand what it takes to optimize and fine-tune that. So when you're doing that cycle many, many times, there are challenges, of course. We've demonstrated 150 cycles so far without any mechanical issues or separation. And so we believe that that's going to be possible to thousands of cycles, and we're working to demonstrate that.
Thanks.
Thank you.
So I've got a two-part question as well. And I think you covered it a little bit around consumables and maintenance. Like, is it something I just drop there and it just works for the next 20 years? Or is there consumables and other things I need to do? It's the first part.
Yeah.
The second part, I know you're fairly early in your development cycle, but are you starting to think about other regions where power is either difficult to get or extremely expensive? So, South America, for example.
Yeah, absolutely. Great questions. So I'll answer the second one first. So just came back from Australia, like I said. What I've come to learn is that, APAC and Australia, this is true about LATAM as well, have tremendous renewable penetration. So Australia has a 40% average renewable penetration across the country. There are regions there that have over 70, 80, even 100% renewables, like South Australia, for example, where there are a number of mines that are grid tied, have power capacity challenges, have tariffs that actually are flexible, so you can get zero cost energy sometimes, and they have no gas connection. If they do have natural gas, that's really expensive. On the east coast of Australia, it's like $15 a gigajoule on average. So, that makes it really, really attractive. So regionally, yeah, there's an absolute potential for this solution in other markets. I mentioned Chile and BHP, for example, leaching and copper production there. Renewables are abundant. They're using diesel. It's remote sites. So absolutely, there's a huge global potential. And we're only talking about mining here, but of course there's 25% of final energy use is actually in industrial heat, industrial processes that go beyond mining. So in food and beverage, pulp and paper, oil and gas, chemicals, all these industries need a vast amount of heat, and those are fair game for our solution as well. You have to remind me the first part of your question, I'm sorry. Maintenance. So yeah, the standard answer to your question is that the balance of plant equipment will have like an O&M regime that's similar to that of other power equipment. So there's no consumables in that per se, but there'll be an operation maintenance regime. The consumable would be the iron if there is a need to actually replace the iron. We've demonstrated economically that 1,000 cycles is what we need for viability. So if we replace the iron at 1,000 cycles, we can actually have a product that still makes money and adds value for the customer. So that's where we're trying to get to. If that is needing changing, then actually the iron cost is a very, very small percentage of the bill of materials. And we can design the solution to have an easy swap out of that iron. So as a consumable, that wouldn't be prohibitive. Yeah, thanks for your question.
All right, thanks, Hayden. I'm curious. We know the lithium market is controlled by specific players around the world. Does using iron brings a solution to that problem, or it's going to be the same issues for the supply chain?
I don't think it'll be an issue at all in supply chain. We've demonstrated on spreadsheets, thousands of megawatts of production per year would only need 0.01 to 0.1% of the global production capacity of iron today. That production capacity can be made clean also. There's technology already existent for that. The same is not true for critical minerals that are in batteries. And obviously the practices around getting those minerals are sometimes challenging. So I don't see that as a constraint at all. This was the essence, the ethos of the company. When Professor Berg-Thorsen was looking for the right material, the first criteria was abundance. And there's no metal more abundant than iron. So.
Okay, thanks for the answer. I'll be just a bit more straightforward also with the question.
Sure.
Can we bring back this supply chain to Canada with iron?
It's a good question. It's probably a question more for the government, the mining companies out there. I believe we can. I think if we can produce a homegrown solution that can solve a lot of the world's challenges around energy that's based on iron, and we're not the only ones doing this. I mean, we're not the only ones using iron as a storage mechanism. So Form Energy is the big American company that's had almost $1 billion of investment. Their solution is also iron-based for the same reasons that ours is. It's electrochemical, it's a lot bigger, so it doesn't really serve the same needs that ours does. But I believe that iron is a ubiquitous solution to solving a lot of the world's energy challenges. So, and if there's a demand for that, making a new output for that iron, why not do that in Canada where there's a vast resource pool of that? And maybe actually making the iron here with iron heat could be a way of doing that as well. Good question.
Thank you. Just one more question. Thanks, Kyle. My question is about scale. Just how big can you make this?
Yeah, that's a great question too. So actually the cool thing about the tech is it's modular and cellular and therefore scalable. So the cells that I showed before, you basically build the product based on a cellular architecture. So a module would feature about 1,000 cells and a module could be replicated many, many times. So that 40-foot shipping container I was talking to you about, which is 35 megawatt hours of stored energy, can release that energy in 1 to 9 megawatts, and then it can scale up in additional containers. So we envision a product that's about 50 megawatts max out of those shipping containers. And for an application like example BHP's potash drying facility in Jansen, Saskatchewan, that project is hundreds of megawatts, 200 megawatts or so. That would actually need a lot more than just 50 containers. And so in that case, we'd build a bespoke construction featuring the same modules, but just replicated many, many more times. So instead of the containers, we just build it into a factory.